This video is to cover the conservation of energy with an Atwood machine. I've already given you an introduction, so this is the diagram again. I expect to see this in your notebook. These are the equations we're going to use, and this is the derivation of the theoretical acceleration. We should be able to follow that. I have two formulas for net force. One is just I subtract all the forces in one direction from the other, and I have the total mass times the acceleration. So that allows me to set those two equal. So m1g minus m2g equals the total mass times acceleration. Then I solve for a and factor my g out. So we should be able to follow that. Again, you're not required to do this as far as on the test, but I want to see in your notebook so you have an understanding of where this formula is coming from. Okay? Because if we work a problem on the quiz, I'm not going to give you this formula. I'll give you this one. And you need to be able to figure out how to get this formula. So now the only data that we've collected, we will measure the height, and then from the lab quest we'll measure the velocity that all the mass was going when it hit the floor. Everything else is calculated. So again, I expect to see row 1. So the first thing for row in my table is to find the change in potential energy of the first mass, which is just mg times the change in height, and I do the same thing for the second mass to find my change in potential energy of mass 2. I think that's pretty straight. Then we found the kinetic energy. Remember, you have to use the total mass. This is the mass of the whole system, so I add them up and I get my velocity that I measured from my lab quest, and I get this for my joules. We're going to ignore the energy in. We're going to ignore that it was negative in the table because we're putting it into the system. So the negative just means that mass 1 lost this energy. Then the energy out, two energies. We raised mass 2 up, so that's the potential energy of mass 2, and we sped up the whole system, which we just calculated how much that was. So we add those up, and this I actually did do this lab for one row at one time, and this was the efficiency I got. Now it's possible that if our measurements aren't quite right, as efficient as this is, you might get over 100%, which we know is impossible. But I would expect us to be in the 90%. Now, if we do more weight, as the weights get higher, we'll have more friction. Okay. Now, it's not an error to not have 100%. We know there's friction in the system. The second thing we need to do is calculate the theoretical acceleration. We just plug it in that formula from the previous page, and in my case it's hard to read, that's 1.11. Then we had the calculated acceleration, which I used this formula. You plug the numbers in, you solve for a, and I got 0.98. Now those look reasonably close, but our accelerations are so small here that it doesn't take much difference to get a 12% error. And we're going to use error because we have a theoretical value that it should be. Except we know there's friction. We know there's going to be an error. We're not going to get the theoretical acceleration, but we're still going to use the error calculation. And those are all the calculations you're going to do. Make sure you do the whole first row once. Make sure your data is reasonable before you collect a bunch of data, because if you do the whole lab wrong, you'll have to redo it. So, have fun. Good luck.